Hello, everyone. I'm glad to present our work, Oblivious Neural Network Predictions. So nowadays, machine learning as a service is a very popular paradigm to provide online predictions. In this service, the server trains the model and receives inputs from the client, and runs the model on the input and returns the predictions. Let's take Google Translate as an example. The server uses the model to translate the sentences submitted by the client. In this case, the client has to review their input to the server. In some scenarios, like online medical diagnosis, the input can be very sensitive. If the server is malicious, it can misuse the data. For example, instead of doing online diagnosis, it can profile the user or sell the data. So a simple solution is to have the client download the model and run the predictions on client side. However, this is not always acceptable. For example, the model is usually considered to be a business asset by the server, and if the client is malicious, it can steal the model and use it to make money. And the client can also probe the model by generating so-called adversarial examples to evade detection. This is not acceptable if the model is used for something like malware detection. And even worse, the client can invert the model and get the training data. So how should we solve the problem? We would like to have an approach that allows client and the server to run the predictions in such a way that the client learns nothing about the model and server learns nothing about input. In our work, we are focusing on the neural network predictions because this is the most commonly used machine learning techniques. So to this end, we ask the question, given a neural network, is it possible to make it oblivious? What I mean by oblivious is that during the prediction, the server learns nothing about client's input, and the clients learn nothing about the model. We are not the first to consider this problem. For example, last year, Microsoft Research proposed a solution called kryptonite. It helps the client encrypt the input using fully homomorphic encryption, and having the server run the model on the encrypted data and return the encrypted predictions. It provided a high throughput for batch queries from the same client. However, it has two problems. The first one is it involves a high overhead for single queries. For example, in the MNIST dataset that consists of handwritten digits, it takes 5 minutes to identify a single character. And second, this technique only supports limited models because fully homomorphic encryption cannot deal with high-degree polynomials or comparison operations. So we present a solution called MiniONN, which stands for minimizing the overhead for oblivious neural networks. We only use lightweight cryptographic primitives such as additively homomorphic encryption and secure two-party computation. As a result, we achieve a low latency, which is around 1 second for a single query. And we support all common neural networks. Next, I will explain the idea of MiniONN by transforming a simple neural network. In this network, the input and the output are vectors with two elements, and it consists of 3 layers. Some layers represent linear transformation, which consists of multiplication with weighted matrices and addition with Bayes vectors. These alternated with other layers that represent nonlinear transformations, such as activation functions or pooling operations. So in order to support all neural networks, we must be able to support linear transformation, activation functions, and pooling operations. This is what I'm going to show next in a few slides. For now, I assume all the operations are in a finite field of size n. Later, I will show how to deal with floating point numbers. So the core idea of MiniONN is to have the server and the client secretly share the input and the output for each layer. That is to say, at the beginning of this layer, each party will hold a share that is indistinguishable from random to that party, and which, if added together, can recover the original input. Then, during the processing of this layer, they will obliviously reconstruct the input, do the operation, and reshare the output. They will do the same thing for all layers and combine the output in the end. So if we can securely evaluate each layer, then the combination of all layers will be secure as well. Next, I will show how to do this processing for each layer. Namely, I will show how to do linear transformations and activation functions and pooling operations. So first, the client needs to initially share the input. To do this, it just locally generates some random numbers, xc, and then calculate server's share as x by calculating x minus xc. Notice that xc is independent of x, so it can be pre-chosen. So to do the linear transformation, we start from the basic matrix multiplication. Then we replace this x with the shares. And then we multiply the shares into the matrix. And then expand it and rearrange it to this format. So the key observation here is that this part can be computed locally by the server. But the tricky part is here. W is only known by the server, and SC is known by the client. They need to obliviously calculate the dot product. We develop a protocol for this task. We first have the server encrypt the element in W using a daily homomorphic encryption and send to the client. And the client multiply xc to W and masked with some random numbers generated by itself, and then return the ciphertext. The server decrypts the ciphertext and add together all the elements that corresponding to each row. At the same time, the client also adds the R values that corresponding to each row. So notice that if we add this V and U, the randomness will get cancelled. The random values will get cancelled. So the result is exactly W times SC. And please also notice that all these U, V, W, SC are independent of the query X. So the whole protocol can be pre-computed. We further improve the performance using a technique called SIMD, which stands for Single Instruction Multiple Data. Because the ciphertext is much larger than the plaintext, so we encrypt multiple elements into a single ciphertext. So now, this part can be easily calculated by add together U and V. And then the server just output this part to next layer, and the client output this part. We rewrite them as YX and YC. Now we have seen how to convert linear transformations into the Oblivious form. Next, let's see how to do this for activation functions and pooling operations. We classify all such functions into two categories. The first category is called piecewise linear functions. We take ReLU as an example. It takes input y and compare y with 0. If y is larger than 0, it outputs y. Otherwise, it outputs 0. So the oblivious format of this function can be easily calculated using a Gabor circuit, a 2PC protocol. The second category is called smooth functions, such as sigmoid. It's a bit more complex. As we all know, it can be approximated by high-degree polynomials using Taylor series. However, it involves a large overhead and accuracy loss. Instead, we approximate it using piecewise linear function. That is, we split these smooth functions into several segments. And then for each segment, we using a linear function to approximate it. And we generate a Gabor circuit for each linear function. Then for each input y, we first which segment does this y belongs to, and then calculate the corresponding Gabor circuit, and multiply with 1. And for other segment, we also calculate the corresponding Gabor circuit to protect the information which segment it belongs to. But we multiply it with 0. And in the end, we add together all the results of all segments. So empirically, 14 segments is enough to get high accuracy. So next, I will show the detail how to approximate the smooth functions. So first, we set an approximation range with n equally spaced samples. And then for each sample, we calculate the corresponding value by applying f. And then we fit an initial linear function to fit all the samples using regression. Of course, this is not accurate. But the important part is we select a switch over point, which is called a knot, to fit two new functions on either side. The switch over point is chosen such that the overall goodness of fit is maximized. Then we repeat the fourth step until the number of linear functions is 12. Remember, last slide we showed that 14 is enough. And then we set boundary functions for y smaller than y1 and y larger than yn. Okay, so in the end, the server just retains his shares to the client, and the client can recover the real output by add them together. Please notice that if the client only care about the maximum value among y1 and y2, they can jointly calculate the maximum value of them using a Gabor circuit. This can minimize the information leakage. Now we have seen how to calculate each layer obliviously. We have several computational tricks. We lift the floating point number to integers by multiplying a constant and drop the fractional part. So in order to do this, we must make sure that all the activation functions or Boolean operations should be order preserving. Fortunately, all the commonly used are order preserving. And second, we use values that are larger than half n to denote negative values. To do this, we must make sure that the absolute value of any intermediate result must not exceed half n. So what if they exceed half n? Then we deal with such large numbers by securely right-shifting them using a Gabor circuit. So for implementation, there are existing libraries for secure two-party computation and homomorphic encryption. So we want to do a head-to-head comparison with CryptoNet. So we train the same model in MNIST using square as an activation function. Our model achieved 1.3 seconds for a single prediction, which is 300 times faster than CryptoNet. If we don't include the pre-processing time, it is 700 faster. And we also want to show that our technique supports more challenging data set. So we train a model in CIFAR10 using ReLU as an activation function. And the model consists of 20 layers. Even though the overhead is still high, but as far as we know, this is the first attempt to transforming such a complex neural networks. We also train another model using this called a Pantry Bank dataset, which is a typical dataset for language modeling. And we're using the original sigmoid as the activation function. But during prediction, we replace it with our approximated version. But we only have a cross entropy loss increased by 0.5, which is very small. So as a summary, we propose a technique that can efficiently transform any given neural network into an oblivious one with no or negligible accuracy loss. Thank you.
I just want to clarify, what information do you reveal? Do you reveal the number of the internal nodes or the graph or neural network graph?
Yeah, we will reveal the structure of the network.
Only weights are protected, but the entire structure is observable.
Yes. The structure will be revealed.
Okay, so do you know the implications of structure based on the other attacks? Like, can we infer something just looking at structure?
Well, this for some cases is not very important because when you have a neural network, like Google has a neural network, he may publish a paper to describe this neural network, but they won't publish their real model, which is trained based on their data. That means the structure of the network is usually public, but the real model is usually kept private.
Thanks.
Yeah.
By the way, I haven't introduced myself. I'm Eileen from Princeton University. I hope it's not too late, but I have two simple questions. How do you choose the constant that you're going to multiply with, the floating point numbers? And the second question is, how do you pick the activation functions?
For the first question, this depends on the network. Depends on the network. Sometimes if we choose a very large, it will affect the accuracy. But if we choose a small constant, it will overflow, and we need to do more shifting, and this is a trade-off. And it really depends on the specific neural network. And for the activation function, we don't choose our activation function. We don't have any requirement on the activation function. For the machine learning expert, they want to train a model, and they just train using whatever they want, and we can transform into an oblivious form.
Thanks, and let's thank our speaker again.
Yeah, one more question.
Sorry, one more question. I didn't see you.
Sadiq Rezi from UC San Diego. I wanted to ask, you mentioned when you have a piecewise linear activation function,
Yes.
you do the multiplication for each part using Garble circuits.
Yes.
I wanted to ask, isn't it more efficient to first multiply each part using homomorphic encryption and then select one of them obliviously using Garble circuits?
Multiply using homomorphic encryption.
Yeah, I mean computing each part,
Yes.
multiplying input with each slope,
Yeah.
and then using Garble circuits to obliviously select one answer, depending which range it resides in?
Well, I'm not sure about this. I think this needs to some more detailed analysis.
Okay.
Yeah.
And the other question is, are the implementation codes available online?
It will be available soon. We want to give a nicer user interface that you can just give this description of the neural network, just input it, and it will give output the model.
Thank you very much.
Thank you.